All right, this video is going to be talking about what we've learned so far about Taylor polynomials and Maclaurin polynomials. And when you find those, we want to talk about how accurate those decimals are, or how far off they could be, or the error that we could find. So we are going to be taking notes on this packet. But before we get to this packet, I just want to kind of give you an intuitive understanding of what it is that we're referencing here. So when we were doing Taylor polynomials and Maclaurin polynomials, we were starting off with some sort of curve. F of x equals sine of x. Sine of x is not considered to be a polynomial. So what we do with this Maclaurin polynomial right here is we're taking this polynomial right here and we're saying, if you want to evaluate these two functions at the same value, then the more terms you have in your polynomial, the more accurate that evaluation is going to be. And that eventually, if you evaluated enough terms, you'd basically have whatever you'd get for sine if you plug it in. So what I did, just to make sure that we understand exactly what I mean by that, is I plugged sine of 0.3 into my calculator and I wrote down all 10 decimals that I could see on my screen. So if I look at the Maclaurin polynomial and I ignore everything but that first term, then when I plug 0.3 into that first term, I get 0.3. And that's not even a bad evaluation, because if we were to round this to the nearest tenth, then 0.3 is the answer we would have gotten. So even though this is just the first term of the Maclaurin polynomial, it's a pretty good representation of what sine 0.3 is. So then, to get a more accurate representation, I said, all right, well, let's take the first term and the second term. So I wrote the first and the second term out. I plugged 0.3 in, and when I evaluated it, I got 0.2955. So now, because I've got more terms of my polynomial being used, my decimals are going to be a little bit more accurate. So my evaluation is a more accurate representation of what the curve actually was, right? If I include the first three terms, then I notice if I plug in 0.3 that my answer here is even more accurate. All right, so in the past, we've looked at this and we've gone like, yeah, if I plug in a couple terms, I feel like that's pretty accurate, good. You know, and then that's it. We move on. We just say it's a good representation. What we're doing today is we're learning about some mathematicians that were they were perfectionists, and they said, well, I can see that it's accurate. I just want to know how accurate it is. I want to know what level of error I can see in this problem. So 0.3, yes, a fairly good representation, but it's not accurate. It's not the exact number. This, again, it's a pretty good representation, but it's not accurate. And they wanted to come up with a way for us to quantify how far off our answers were. And that's what we're doing today. So if you look at your notes, this idea of how far off our answers are called the error bound. If you took AP statistics, it's going to kind of remind you of confidence intervals. If you didn't take statistics, don't worry about it. So, sorry, looking for my pencil. All right, so the error bound gives the largest possible error in an estimate. The largest possible error in an estimate. The actual error is going to be less than the bound. So we're going to say the real answer is somewhere between this and this. I don't know exactly what the real answer is, but I know it's between this and this. And when we give the actual boundaries, we're being conservative with those boundaries. We're erring on the side of caution. So we're saying our answer is going to be, is probably more accurate than we're giving it credit for, basically. There are two types of error bounds. One is alternating series. And the other is Lagrange. So alternating series, for that error bound, we're going to look at that first because it's pretty simple. If a series is alternating and decreasing, so we know it's alternating because it has -1 to the n or -1 to the n plus 1 as part of the series. We know it's decreasing if, as you plug in consecutive terms, your term gets smaller. So maybe you have the series like 1 over n. So you plug in 5, you get 1/5. You plug in 6, you get 1/6. You're like, okay, those numbers are decreasing. So that's what I mean, is they're alternating between positive and negative, and if you look at the terms, they're decreasing as you go. the error bound in the worst case scenario, so again, we're saying we're being conservative here. We're erring on the side of caution. The worst case scenario can be found by taking the absolute value of the next omitted term. The next omitted term. All right, so this says find the error bound of using the first 5 terms to approximate f of x when f of x equals this stuff. So we're going to find the first 5 terms. So the curve f of x, I don't know what the curve is, if it's a sine or a cos or an e to the x or a combination of those or what. I'm not sure what it is, but they're using this to help us come up with the terms for it. So if I plug 1 in, then my exponent is even, so that's going to make this positive. So it's positive 1 over 1. If I plug in 2, then this is going to be an odd exponent, so it's going to be negative 1 over 2. If I plug in 3, this is going to be an even exponent, so that's positive 1 over 3. If I plug in 4, that's going to be an odd exponent, so that's negative 1 over 4. And if I plug in 5, it's going to be an even exponent, so positive 1 over 5. So those are the first 5 terms. All right. So now we're going to say that the error, and what we would do is we would find the sum of this, we would add up all those terms, we'd get some sort of answer. And I would say that answer is the actual decimal of, so we're going back to thinking of it this way. This answer that I got right here is the actual decimal of this with an error that is less than or equal to, the next term would be 1/6. All right, now you're probably looking at that like, Ms. Rice, the next term is not 1/6, it should be negative 1/6. But notice my error isn't an absolute value. All right, so I'm saying if you were to add up all these numbers, that this would be the actual number that the curve, the actual decimal that the curve is, with a level of accuracy of 1/6. So it could be 1/6 above the actual number or 1/6 below the actual number. That's what it's saying. And that's a conservative guess. So it's probably closer than 1/6, but that's our conservative guess. Now here they're saying find the error bound if there are 99 terms. So now we're going to say the error is less than or equal to 1/100th. So 1/100th is a lot closer to the actual answer than 1/6, right? So it's saying if we added up all the first 99 terms, then that would be real close to what you would actually get if you plugged it in the curve. The level of error that you could possibly have is you could be 1/100th under the number or 1/100th above the number. And so the more terms you have, just like we're looking at here, the more terms that we had in our polynomial, the more accurate our decimal is going to be. All right. So here they're saying how many terms do we need to add to have an error that is less than 0.00005? So I'm going to say that my goal is that my error is less than or equal to 0.00005. Although it just says less than, so we shouldn't say equal to, we're just going to say less than. Okay, so the error that we want is that 0.00005. And the way that we calculate that is we take, so if we ended on the 5th term, we do the 6th term. We're saying we ended on the nth term, so we're going to do the nth plus 1 term. So underneath here, this says n for nth term, and we're going to do the n plus 1 term. And then again, the error is an absolute value. So even though this series alternates, I'm taking the absolute value of that, so the top is going to be positive 1. So I just took this, and I'm thinking this represents the nth term, so I want to do 1 more than that. All right, now I'm going to go ahead and solve this for n, because n is the number of terms that I need to add to get to that error, or that level of accuracy basically is what we're looking for. So if I need to solve for a variable that's on the bottom of a fraction, then I just need to take these two things and have them switch places. So n plus 1 to the 6th power is 1 divided by 0.00005. If you divide this on a calculator, you're going to find that that is 20,000. So next, to solve for n, we're going to go ahead and take a sixth root. So I've got n plus 1 equals the sixth root of 20,000, which is approximately 5.210. Then I'll go ahead and subtract 1, so I have n is approximately 4.210. So at the 4.210th term, your level of error is going to be less than 0.00005. So you've got the right answer. It could be 0.00005 below or 0.0005 above your decimal, but you're accurate within that. And here we obviously can't have the 4.2th term. That's not possible. So if you round down and you look at the fourth term, your answer is going to be less accurate. If you round up, your answer is going to be a little bit more accurate. And here we're not saying we want to be any less accurate than this. So that means we have to be a little bit more accurate than we're getting from this number here. So more accurate means we got to round up. If we round down, then this number is going to be a little bit higher because you're going to be less accurate. So we're going to say we need 5 terms to be able to hit that level of accuracy. But when you do 5 terms, you're actually going to be a little bit more accurate than we wanted. So that's okay. All right, so if you look at this, the common sense of what we're doing here is we're saying if you want to actually find the perfect decimal, the decimal that you actually should get if you plug in sine, and you don't plug in the polynomial, you plug in sine of 0.3 and you get the real decimal, then for us to be able to get that decimal from the polynomial, we're going to plug it into the polynomial right here. If you recognize this, this is Taylor's polynomial right there. So plug it into Taylor's polynomial and get this answer, and then add or subtract off whatever your error is, and then you have the perfect answer. All right, so this part we're adding or subtracting off here is however far you are a little bit above or a little bit below, but this is the little bit of error bound that you have, and this is what we call the remainder. All right, and the remainder is found, and this is just like the alternating series. Let's say you stop at the 5th one, then the next term, just like we set up here, is if we stopped at the 5th term, we're going to do the 6th. If we stopped at the 99th, we're going to do the 100th. So here, if we stop at the nth, then we're going to use n plus 1 to help us figure out what our error bound is. And you can see that the way we're calculating this is the same as what we've always done for the Taylor series. So we have the derivative of the n plus 1th term evaluated at something, and then we have x minus c to the n plus 1, and then n plus 1 factorial on the bottom. So you'll notice that this is very similar to what we just did. All right? So there's a little bit of history involved here. It's called 2 different things. It can be called Taylor's theorem remainder because it takes the Taylor polynomial and it adds a remainder to it. But people often call this the Lagrange error bound because Taylor, if you flip the page, the history of this is that Taylor introduced his formula for the polynomials in 1712, and Lagrange 85 years later came up with this error bound thing. So it used to be that when they plugged the numbers in, they looked and they said, 10 decimal places of accuracy, sweet, that's a good number, and they felt good about it, good feeling numbers. They're like, those are pretty approximate, we're okay with that. And then you run into Lagrange, who's maybe a little bit more of a perfectionist. He said, yes, the numbers are good, but they're not perfect, and he wanted to quantify how far off they were. And so that's where the remainder came from, is this idea of quantifying how far off your answer is. All right? So we want to figure out how to calculate these. And so we've got a few different parts of the remainder. So if you recall, what I just referenced is that they look like they come from the Taylor series. So we've got something right here. And sometimes this will be given to you and sometimes it won't. And then we have the x. They put an a there because they're saying you're going to evaluate it at some value. So if you're evaluating it at 0.3, like for the example I showed you at the beginning, and you plug 0.3 in there. C, again, is the number you're centered at. So for a Maclaurin series, it's centered at 0. For a Taylor series, it could be centered somewhere else. And then for the n plus 1s, we'll know what that number is because it's just whatever the next term is. Okay? So let's go ahead and do this. This first problem is saying that we're evaluating our function at 3. It's saying that they have done a 4th degree, so that means when we do our error, we're going to have a 5th power in there. And it's centered at c is 2. So let's go ahead and think about plugging all those things in. I have the error is less than or equal to, and the formula says I'm going to take the 5th derivative. Since this is a 4th degree, I have to go up by 1. 5th derivative, and I'm going to be plugging something in here. I don't know what they plugged in. If you look in here, you can see that they put a z in for that sometimes. And then we're going to have x minus 2 to the 5th power over 5 factorial. So again, the reason I knew that I was using 5s in all these places is because this said 4th degree and I'm going up by 1. So now I'm going to rewrite by plugging in information that they have given to me. So they didn't tell me what the z is that we plugged in, but they did tell me that whatever it is we plugged in, we got 0.3. And it says less than, so I'm not going to keep saying less than or equal to, I'm just going to say less than. We got 0.3 times, and now I can go ahead and plug in, or not 2, sorry, we're evaluating it for 3. So now I can plug in the 3, because that's what we're evaluating it for. Okay, and then you can plug this into your calculator, and if you plug that into your calculator, you find that the error is less than 0.0025. Okay. So now what they're saying next is they're saying, all right, suppose you take your polynomial with 4 terms. So suppose you're taking this one right here. Only, let's pretend there's one more term. And you plug in the number and then you get some sort of answer. They're saying this is the answer that you're getting. Now they're saying take your error up here, so we know the error is telling us that this is correct, but the actual decimal, the decimal for the actual curve, this thing right here, could be 0.0025 below this decimal, or it could be 0.0025 above that decimal. So I'm going to say that the actual function evaluated at 3 is somewhere in between this decimal that I got when I plugged it into my polynomial minus the error bound and this decimal plus the error bound. And again, these error bounds are giving you conservative estimates. So they're saying this interval is a little bit bigger than it needs to be. We just want to make sure that we really got it. So we're going to say that f of 3 is somewhere in between 1.7605 and 1.7655. So I don't know exactly what it is if you were to have the actual curve, not the polynomial, but the actual curve and be plugging it in, but I do know it's somewhere between these two values. So is it possible that the real curve could equal 1.768? The answer is no, because 1.768 is not in between these two values. All right, then they want to know, is it possible that the actual curve evaluated at 3 could be 1.761? And so we look, 1.761 is in between those values, so we're going to say yes. All right. So what they're saying next in this little important notice here is that sometimes the value, we had 0.3 for this, sometimes this value is not explicitly given or easy to find. So sometimes they don't tell you what this number is, they don't tell you what the z is, so you can just plug it in and find it. And in this case,
we may choose the first known reasonable rational number that's greater than that. So we're choosing something that's a little bit too big. This means round up, a little bit greater than that. So this means that if you have a situation, you got to round up. Because we want our error bound to be a little bit too big. We want our interval to be a little bit too big, so for sure the answer's in there, rather than be too small. If we choose a number that's too large, we defeat the purpose of the error bound. If you're saying my answer is somewhere between 1 and 100, it's like, yeah, there's a lot of answers between 1 and 100. But if we choose a value that's smaller, then there's no guarantee that our approximate answer is actually accurate, that it's actually somewhere in that interval, okay? So this just means that we are taking the first known reasonable rational number. So rational number means like rational numbers are ones that can be written as fractions. All right, so round up. Okay, doesn't mean a lot to you now, but if you highlight it, underline it, star it, whatever, we're going to come back to that and it will mean more in a second. Okay, so the next example, we're going to our sine curve here. And it says find the 5th degree Maclaurin polynomial for sine, and then use this to approximate sine 1. So the 5th degree polynomial for sine is x minus x to the 3rd over 3 factorial plus x to the 5th over 5 factorial. So if we're going to use that to approximate sine 1, then that's going to be 1 minus 1 to the 3rd is just 1. So I've got 1 over 3 factorial plus 1 over 5 factorial. All right, so if you plug that in, you're going to get 0.84167. 0.84167. All right, so we came up with our approximation. Next, we want to find the error for our approximation. So I'm going to do my formula. The error is less than or equal to. The next term, even though 6 is the number that comes after 5, we know that the next term here would be 7. So I'm going to say f7 of z times x to the 7th over 7 factorial. Now, if you guys remember where the Maclaurin series came from, when you did the derivatives and you evaluated them, they either ended up equaling 0 or 1 or negative 1. So we know that this value right here would be a 1. So on the top, I'm going to have 1 times. And then we're plugging in a 1. We evaluated it at a 1. So this is 1 to the 7th over 7 factorial. So our error is less than or equal to 1 over 7 factorial. All right. So this, they said to find the maximum error for our approximation and to give that to 5 decimal places. So what they mean by maximum error is they're saying like how far off is your answer. So if we used all these terms and we plugged in 1, how far off could our answer be? It could be off, it means I need to take my decimal and move it 4 places to the left. So it could be off by 0.1, 2, 3, right? So move it over once and then 3 more times. 2, because I'm rounding the 1 up to a 2 because it's followed by a 9. All right, so this is our maximum error. At the most, our answer is either 0.0002 too high or 0.0002 too low. So that means if we want to find the interval, then we're going to say that sine of 1 is in between 0.84167 minus 0.000, well, it said 5 decimal places. 20. Yeah. Sorry. The 19 is followed by an 8, so it'd be a 20. 20, and then 0.84167 plus 0.00020. So we have 0.84137 and 0.84177. So the actual answer is somewhere in between those. All right. Is it possible for sine 1 to equal 0.87? No, definitely not. 0.87 is not in between. .84137 and 0.84177. The answer is too big. All right. Next example says write a 4th degree Maclaurin polynomial for e to the x. So e to the x using the Maclaurin polynomial is 1 plus x squared over 2 factorial plus x to the 3rd over 3 factorial plus x to the 4th over 4 factorial. Okay, so here it says to approximate square root of e. I'm going to rewrite that because these are e to an exponent, so I have to rewrite this as an exponent. That's e to the 1/2. So they want us to plug 1/2 in for x. So e to the 1/2 is approximately 1 plus 1/2 plus 1/2 squared over 2 factorial plus 1/2 to the 3rd over 3 factorial plus 1/2 to the 4th over 4 factorial. And if you plug that in, you'll notice here that since we're rounding in the middle of problems, we're using more decimal places. So typically in calculus we do 3. Here we're doing more like 5. I would say that's a good general rule, is that when you're doing these problems to round to 5 decimal places. So this is 1.64844. Okay, so if we're going to calculate this, they said the maximum error needs to be when x is less than or equal to 0.5. So what they mean by that, I'm going to go ahead and write the formula for error. So the error is less than or equal to f5 of z, and then it would be x to the 5th over 5 factorial. So for this one, they're actually telling us what we should plug in here. They're saying when x is less than or equal to 0.5. Now this is when we're going to reference this part of the page where we say, in this case, we're going to choose the first known reasonable rational number. So we're going to go ahead and evaluate e to the 0.5. That's kind of funny because that's your answer. Anyway, so this is 1.64. And we're going to go ahead and round that up to 2 because we're going to the first reasonable rational number that's above that. So we're going to say 2, and then in here, the x is asking us to plug in 1/5, or sorry, 1/2. That's what we're evaluating this at, divided by 5 factorial. Okay. And then again, I'm going to go ahead and do 5 decimal places. So the error is less than or equal to 0.00052. All right, so if we want to write our interval, we're going to say, in this part it says no calculator. It's lying to you. Okay, So if we write our interval, we're going to say that square root of b is somewhere in between this decimal minus this error, or this decimal plus that error. So 1.64792, 1.64896. Somewhere in between those two numbers. All right. So here for example 6, it says, write the third degree polynomial. So we have, and it's centered at 2. So our first coefficient, we've got 6 plus, the second one, 4. 4 times x minus 2 minus 7 times x minus 2 squared over 2 factorial plus 8 times x minus 2 to the third over 3 factorial. And we're using that to approximate the function evaluated at 2.3. So if you plug 2.3 in, you get 6.921. That's not a rounded number, that's actually what it gives you. Okay, so it says the fourth derivative of f satisfies the inequality this. For all the closed interval, the Lagrange error bound, we're going to approximate 2.3. All right, so we're going to say error is less than or equal to f4 of x times x minus 2 to the fourth over 4 factorial. And then if I plug my numbers in, I'm going to say that the error is less than or equal to, and they told us that this was less than or equal to 9. So 9 times x minus 2, we're plugging in 2.3, 2.3 minus 2 to the fourth over 4 factorial. And when you plug that into a calculator, you get that the error is less than or equal to 0.003. I went ahead and rounded this one to 3 decimal places because this was to 3 decimal places. So I'm just, and that one wasn't rounded to 3, it just happened to only have 3. All right, so my interval, the actual curve evaluated here, would have been somewhere between 6.921 minus 0.003, 6.921 plus 0.003, somewhere in between those. So it's somewhere in between 6.918 and 6.924. So, is it possible that the actual curve evaluated at 2.3 is 6.992? No, 6.992 is too big. So no, 6.992 is not between